VLSos here. This is a video lesson on geometric series. Let's take a look at something. 6 plus 12 plus 24 plus 48 plus 96, and this keeps going. We have a series because it's not simply a sequence of numbers, we're adding them together. We could analyze this series to see if there's a pattern that generates the term values. We could start with 6 and think, how do we get to 12? We add 6. But do we add 6 to 12 to get 24? No, so it's not arithmetic. What's another way to get 12 from 6? We multiply by 2. Does that rule hold carrying forward? 12 times 2 is 24. 24 times 2 is 48. Yes. So the rule is to multiply by a constant ratio, in this case, positive 2. When a sequence or series has a rule that involves multiplying or dividing by a constant ratio, then we call it geometric. More that can be said about this series. It goes on forever. We're not going to think of the sum of all the terms because there's an infinite number of terms. So it would produce a sum that was infinitely large. We can write the value of the initial term, t sub 1, or the value of term number 1, and we could observe that to be 6. We also have a way of writing an equation to find the value of any term number of a geometric sequence or series, and that equation is the value of the initial term, in this case 6, times the constant ratio multiple times. We write repeated multiplication as a power, so in this case it would be 2 to the n minus 1. We subtract 1 from n because we don't multiply by the constant ratio to find the value of the first or initial term. Now, there is an alternative equation in this case to find t sub n. The value of the first term, 6, is the product of 3 and 2. So if we included that and then used power properties to combine this factor of 2 into this power so that we add 1 to the exponent, then in this case we could say t sub n is equal to 3 times 2 to the n. Generally, most people use the first equation for term values of a geometric sequence or series. And in general, that equation is t sub n is equal to the value of the initial term, t sub 1, times the constant ratio to the n minus 1. And that, in general terms, is very useful information. If we were to take the sum of a geometric series, in this case, it's expanding forever, so it would only make sense to find a sum of a finite set or a limited set of term values. In this case, S sub 4 stands for the sum of the first 4 terms of what I have here, this series. We have an n value of 4, and that means that we are asking S sub 4 to be 6 plus 2 plus 24 plus 48. The first 4 terms. We can easily add those by hand, but I want to show you an equation to calculate the sum of the first n terms of any geometric series. And that formula is S sub n. It's a little bit sophisticated, so it is beyond the scope of this lesson to show where it comes from. But the sum of the first n terms of a geometric series is the constant ratio r times the value of the nth term or the last term minus the value of the initial term divided by the constant ratio minus 1. And there is an alternative equation to find the sum of n terms. There are 2 equations. They're a little bit different. They're both fairly sophisticated. The other equation is the value of the first or initial term times 1 minus the constant ratio to the nth divided by 1 minus r. And it's no mistake that these differences in the denominator are switched. These formulas are fairly sophisticated, and the difference in their use generally is if you have the value of the last term, sometimes you don't, use the first formula. If you do not have the value of the last term, then you can go with just the first term, constant ratio, and n. So in this case, for this series, if I wanted to find the value of the first 4 terms with these formulas to practice, it would look like this. I have an r value of 2. So S sub 4 is going to be 2 times the value of the last term, which I know to be 48, minus the value of the initial term, which I know to be 6, all divided by the constant ratio again, minus 1. Or, using the alternative equation, the value of the initial term, 6, times 1 minus the constant ratio 2 to the nth, in this case n is equal to 4, all over 1 minus the constant ratio 2. Continuing our work, 2 times 48 is 96, minus 6 is 90, and then we're dividing by 2 minus 1, which is 1. So that is 90 divided by 1, or just 90. Using the alternative equation, we're going to start with the power 2 to the 4th, 16. 1 minus 16 is negative 15. Curious that it's negative. 6 times negative 15 is negative 90. But if we're dividing by 1 minus 2, 1 minus 2 is negative 1. So it'll be negative 90 divided by negative 1, which turns it back into positive 90 and checks with the previous answer. So we have a formula, 2 of them, to calculate the sum of a geometric series. Both of these are useful in different contexts. Let's provide one more example. In this case, we're going to start with an equation. T sub n is equal to 30 times 1.2 to the n minus 1. This formula must produce terms that are geometric because it's the form of a geometric equation. We have a growth factor or a constant ratio of 1.2. And we have an initial term, or t sub 1, equal to 30. If we put 1 into this equation, we would be left with the 30. We could continue and make a table of n values and the values that are produced by the values n. Put the first 3 in, we would get the initial term to be 30. The second term would be putting 2 into this equation, or we could take the previous value of 30 and multiply by the constant ratio 1.2 and get 36. The value of the third term is 43.2, and we could carry this out and imagine that we are using the formula to calculate the value of the 37th term, which a calculator would really help with, and it is 21,264. The reason why I carried this example out to the 37th term is we could imagine that we would be given the project of finding the sum of the first 37 terms. And that's enough terms that listing them all out and then calculating by hand would be too tedious. We want to take advantage of the formulas. In this case, I have the value of the final term and the initial term, so I'm going to use the first formula to find S sub 37. It's going to be equal to, in this case, the constant ratio 1.2 times the value of the final term, 21,264.056 approximately, it's been rounded to the nearest thousandth, minus the value of the initial term, 30, all over 1.2, the constant ratio minus 1. it would be helpful to use a calculator to simplify this, multiply, subtract 30, and then divide by 0.2. And if we did use a calculator, the result would be 127,434.337. Again, an example of starting with an equation that produces a geometric sequence and then thinking of it as a series and applying a sophisticated formula. Last thing to say, take a look at something like this. Or something like this. Very often when working as a student with series and sequences, we get the impression that since all of our examples are designed to practice the formulas and the patterns, that all sequences in series must be either geometric or arithmetic. That's not the case. Taking a look at what we have here, we can see that it is a series because we're adding terms. And then we would go through a process of analyzing what generates this sequence, this series. And in doing so, we would test whether it was arithmetic. Do we add 2 each time? No. We go through the process of finding if it was geometric. Do we multiply by the same thing each time? We don't. This series does follow a rule, but it's not geometric or arithmetic. So noticing that is important because we cannot use the tools and equations and patterns for geometric or arithmetic sequences in series if they are not geometric or arithmetic. So we need to be careful and not make assumptions. This series does follow a rule. I'm not going to tell you what it is. Maybe you're interested in finding it out. And because it follows a rule, we would be able to use that knowledge to find patterns and possibly sums, but not the equations because they wouldn't apply. Take a look at this second list. It's not a series. We're not adding these terms. We're simply listing them. So it's a sequence. And it would be natural to then think, is it arithmetic? It's not. Is it geometric? It's not. So what's the rule to generate the terms? That doesn't have one. So we can't reliably use any knowledge about patterns if there is no pattern. So we cannot use equations or patterns. It is possible to have a sequence or series and have it follow no rule at all.